Hertz. How are you doing today?
I'm doing great, Ron. Thanks.
Awesome. Thank you so much for your time today. And there's so much to talk about, so let's jump right in. First up, can you tell us a little bit about what inspired you to get into astrophysics and a little bit about your history with NASA and the Science Mission Directorate?
Oh, that'd be great. So when I was a little kid, I was really interested in astronomy. I drew pictures of all the planets, and there were 9 at the time. Cut them out, pasted them on my walls, had solar systems all over my room. I got the Astronomy Merit Badge when I was a Boy Scout, loved looking up at the night sky. And then when the space program started up, I was just totally hooked. I remember coming home from school when John Glenn flew around the world, and when the astronauts walked on the moon. Of course, I stayed up and watched that. And my father was a big fan of the space program too. I grew up in Atlanta, Georgia, and we drove down to Florida and watched the astronauts blast off to the moon when I was in high school. And so, you know, that just totally jazzed me for astronomy and space science and the whole astronaut thing. And so when I went off to college, I majored in physics, and then I went and studied astronomy. And you know, I've been a research astronomer, and I got a chance to work for NASA, and I just jumped on it.
That's amazing. And I mean, really, who can blame you? But I know you have dual degrees from MIT, and then you got your PhD in astronomy from Harvard, correct?
That is correct. Yep.
So you're basically one of the smartest people on the planet. Okay, we got that. Kind of reminds me of the scene from the Michael Bay movie. What was it? The one with Bruce Willis and everyone in it, where he says pretty much the smartest person on the planet. So next up, I just want to dive into Kepler and its discoveries. You kind of talked about that at the 2016 Mars Society convention, and just had everyone in the room excited about it. Even though everybody there loves Mars, it's kind of fascinating to hear what's going on. So before we get out too far, I want to talk a little bit about one of the biggest announcements this year, and that was the possibility of the water plumes on the Jovian moon of Europa. So could you tell us a little bit about what that means, and will that fast track the Europa mission that was scheduled for the 2020s?
Well, you know, the reason why everybody's excited about Mars is because it's the closest possibly habitable planet. Mm-hmm. And we know that on the Earth, every time that we have found water and we have found nutrients and we have found energy, then we find life living in that niche. And there's just all sorts of weird niches, habitable niches on the Earth where weird life has arisen. And so in order to look for life, and that's what we really are doing, we're looking for life somewhere else in the universe, whether it's on Mars or Europa or on planets around other stars. That's the ultimate goal, to see if life arose elsewhere other than on the Earth. So we want to look for places where there's water and nutrients and energy. Mars is the closest one. But we also know that there is an ocean underneath the ice on Europa. We know there's energy there because that's the tidal energy from Jupiter is what keeps that water liquid. If there are nutrients in there, then you have an environment where life could have arisen independent of Earth. But it's under miles and miles of ice. The plumes indicate that some of that ocean might be geysering off into space. And so if the plumes of Europa are real, then we might be able to touch the water without drilling through the miles and miles of ice. That makes it so much easier to go to Europa with a robotic spacecraft and try to learn whether it's a habitable environment and whether there ever was life or whether there might be life in that European ocean. So that's why it's an exciting place to go. The recent Hubble results, which provide additional evidence that the plumes are real, you know, give us that motivation to think that we might be able to touch the water without drilling through the ice. The National Academy of Sciences, last time they looked at planetary science and thought about what were the most exciting missions to do, their 2 highest ranked missions were a mission to go to Mars to look for life on Mars, and a mission to go to Europa to start studying that habitable environment. NASA is working on such a mission, a Europa flyby mission, and we're working towards a 2022 launch date, and you can't do it any faster than that. That's just, there's a lot of work to do to design and build and test and launch a mission like that. You've got to do one step before you can do the next step, before you can do the next step, and no matter how much money you have, you just got a bunch of serial tasks, and it's going to take us till at least 2022 to get that mission ready to launch.
It's still exciting though. There's so many people. There's so many possibilities for life out there just in our solar system alone that we found out in the last few years, and within our lifetimes, we're probably going to see NASA, especially, prove life out there. And I think that's one of the biggest things. That'll be one of the greatest discoveries humankind has ever made. So I'm really excited about those discoveries. And next up, we're going to go out a little further because of all the exoplanets. You guys actually doubled the number this year with Kepler. And can you tell us a bit more about that big announcement earlier this year, and if there's been any new updates since then about the discoveries that Kepler's found?
So, of course, I bet most of the people watching know that Kepler is our space telescope that is searching for planets around other stars. And the way it works is it stares at stars continuously, looking for small dips in their brightness caused by when one of that star's planets passes in front of the star and blocks out a little bit of that starlight. But there's other things that can cause dips in the brightness of a star. So when Kepler sees the dip in a brightness, we could call that a candidate, because it might be a planet or it might be something else that can cause a dip. And then we do follow-up observations and eliminate all the other causes of the dips before we declare it a confirmed exoplanet. And we had confirmed about 1,000 exoplanets before May of this year. In May of this year, a very clever scientist figured out a way of analyzing just the Kepler data to look at the shape of the dip in the light from the star, and to match that with all the things it could be, and to find the ones that had a 99% chance or better of only being possible of being a planet. And so he found over 1,200 candidates that couldn't be anything else, but it was only based on the Kepler data. So this was a new way of confirming these candidates. And so, right there we went from under 1,000 to almost 2,300 Kepler candidates. Now remember, amazing. Kepler's not the only way of finding exoplanets. And I just looked up the numbers today. So since May, we found another 62, we've confirmed another 62 exoplanets that were discovered by Kepler. We've also confirmed another 107.3 that were discovered in Kepler's extended mission called K2. But on top of that, we've confirmed a bunch of exoplanets that were discovered from the ground. And the total number of confirmed exoplanets right now is almost 3,400. So that's what we're up to now. So it's, you were talking about the 2,300 we had from Kepler, but it's really about 3,400 right now from all the ways humanity is using for finding planets around other stars. And if I can just jump in with answer a question you haven't asked me yet, Ron. Yeah. By noticing how often we see planets around stars when we look, and they have to be, just in the right place for us to see them, or else they wouldn't pass in front of the star and block out the light. And by estimating what fraction are there that we don't see because their orbits aren't right, we think that pretty much every star in the sky has planets around it. And maybe 1 out of every 5 has a rocky planet that might be in the habitable zone where liquid water could exist on the surface of that planet. So that means over 1 billion possibilities for life as we know it, right, on a rocky planet with oceans, to have arisen just in our galaxy alone. And of course, we all know there's billions and billions of galaxies.
Yeah, that gave me chills already, and I think that's really kind of one of the big things. That's what fascinates most of us is what else is out there, and that's one of the things that Kepler is answering that question. And actually, you kind of mentioned the dips in the starlight, and there's one that we've seen that's been kind of particularly fascinating this year. That everybody's been looking at KIC 8462852 or Tabby star, and it's kind of fascinating because these dips have been really large and nobody can really explain it. It would be much bigger than even Jupiter, just this massive, massive dip. And could you tell us a little bit about what makes this star especially fascinating to deep space explorers like yourself, and what Kepler's role is in trying to figure out just what's going on around this star?
So what makes Tabby's star really interesting is that it's exhibiting a behavior that we hadn't seen before, and as far as I know, we haven't seen since. As far as I know, it's a one of a class. I'm sure, well, it's one of a class. And what it has is it has irregular dips in its light that are as big as 20%. So like you said, that's too big to be a planet, but also they're irregular. Sometimes it dips less than 20%, sometimes, and then they don't come regularly. They were seen by Kepler twice, once in 2011 and once in 2013. Kepler can no longer look at Tabby's star because of the problems with the gyros. It looks in a different part of the sky than where Tabby's star is. So we won't be getting any more Kepler studies of Tabby's star. All we have are those light curves that we got, and we don't know what could cause those kinds of dips. Other NASA telescopes have looked at Tabby's star, including the Spitzer Space Telescope, which is an infrared sensitive telescope, was looking for infrared emission from around the star that might be there if there were a lot of dust around the star. So some of the hypotheses of what's causing those dips might be asteroids or comets around that star that are swarming and colliding. If that were true, they break up and give off dust, and then we'd see the infrared light. We didn't see the infrared light, so that's probably not the right explanation. At the moment, astronomers actually do not have a good explanation that all astronomers agree makes sense. There's a bunch of ideas that that one person thinks is a good idea, and everybody says that's such a low probability of happening, I'm not going to buy into that hypothesis. Which is one of the things that makes science fun, right? You know, I got into science because I wanted to find problems that people didn't know the answers to, and then work really hard on them and be the guy that figured out the answer. And so, you know, there's a lot of astronomers who are trying to figure out, okay, what kind of observation, which telescope do I use, what data can I gather that will crack open this problem and help me figure it out? It's just, right now it's an open question in astronomy.
And that's one of the reasons that so I'm new to the science field. I just started college myself, and this is a dream that I'm chasing for the next 10 years. And it's the question that I always ask myself: what else is out there? What are we looking at? What is that? And that's always, it's that quest to answer those unanswered questions that drives us all. And I think it's kind of amazing that we have this, you know, just this one thing that nobody can agree on. The most brilliant people in the world are working on it, and everybody's like, we don't know. And I think that it's kind of incredible.
I'll make a prediction here, Ron. I'll predict that within 5 years we figure it out.
No, I'll be
paying attention.
We don't know what it'll be yet, but we know it's coming.
There's a lot of people working on it. We have a lot of powerful telescopes. Somebody will make the observation that gives us the clue we need to figure it out.
That's perfect. And speaking of powerful telescopes, another one of the major talks at the Mars Society convention was talking about my personal one, the one that I'm watching. Just I saw the documentary on it not too long ago. It was the James Webb Telescope, and this one's going to blow us away. Many people have talked about we're going to be able to see back to the beginning of time. Basically, that's what this is going to be able to do. So, could you tell us a little bit about the James Webb Telescope, its mission, and any updates? I know we're getting close. It's coming within the next year or two. So, could you tell us a little bit about that?
Sure. The James Webb Space Telescope is NASA's next large space telescope. It's got almost 8 times the collecting area of Hubble, so it'll be 8 times more sensitive than Hubble. It's 6.5 meters across, where Hubble is 2.4 meters across. And 6.5 meters is so big that a mirror that big doesn't fit on top of a rocket. So in fact, the James Webb mirror is made up of 18 hexagons that fit together to make a large mirror. But at launch, it's folded up like origami, so it'll fit inside of the rocket. After it gets into space, we'll unfold it to deploy the full collecting area of the James Webb Space Telescope. But the other thing that's different than Hubble, besides it being so big, is that it's optimized for the infrared part of the electromagnetic spectrum. Hubble is optimized for the optical, the same as our eyes. James Webb will see longer wavelength light that our eyes can see. And so it's sensitive to things that are cooler. But also, as I'm sure your listeners know, the universe is expanding, and that causes things that are far out in the universe to be redshifted. As they're moving away from us, their light gets stretched out, makes the wavelengths longer. So things which are optical nearby look like they're infrared when they're at the distant parts of the universe. And that's where James Webb is the most powerful. We sized it to be big enough, and we picked the right instruments so that it will be able to detect the redshifted light from the very first stars and the very first galaxies that formed, you know, just 500 million years after the Big Bang. Because we want to see how the universe grew from the, you know, the hot maelstrom of energy and atomic matter that was present after the Big Bang into the very organized stars and galaxies that we see in the modern universe. And by looking back in time with James Webb, we'll be able to sample all those stages of the evolution of the universe and see how the first galaxies formed, how those galaxies merged to make larger galaxies, how clusters of galaxies came to be, maybe where the black holes formed. You know, here's something. It seems like every galaxy we look at has a big black hole in its center. Well, we don't actually know which came first, the black hole or the galaxy. That's something that James Webb will help us figure out about how galaxies grew in the early universe. The other thing that James Webb is going to be very good at, and we didn't think about this when we designed it, but it will be able to look at exoplanets as they pass in front of their star, blocking out a little bit of the starlight, like that's what Kepler saw, but that starlight will pass through the atmosphere of the exoplanet, and that atmosphere will absorb some of the light from the star. With our spectrographs on James Webb, it will be sensitive enough that we can take the spectrum of that light, figure out what colors are missing, and we'll know what are the molecules in the atmosphere of that exoplanet. So with James Webb, we'll be able to sample the atmospheres of planets around other stars and see if they have some of the interesting molecules that might, that are interesting on Earth, like methane, carbon dioxide, water vapor, ammonia, these kinds of molecules.
That's amazing. So again, you know, it's another more hints at life and what else might be out there, and those fascinating things. You know, carbon-based life forms are what we know so far, but I think one of my favorite ones is, you know, Titan, and it's so with Titan we have those methane lakes there. You know, what would life like that be like? And then you keep going out, and what else can be out there? And you know, to be able to see these things is going to be amazing. It's one of the reasons I've got an eye on it, and I know that's not the only one. Now that it's past a certain percentage of completion, you all have started working on the next telescope, the WFIRST telescope. So could you tell us a little bit about that and what its mission will be, maybe how it's going to differ from James Webb?
Sure. Well, James Webb is right now being assembled and tested, and we'll be launching it in October of 2018, which is 2 years away from now. But we've already started working on the mission that will the large space telescope that will come after James Webb, and that is the Wide Field Infrared Survey Telescope, WFIRST. And WFIRST has a mirror that's the same size as Hubble, but instead of it being a narrow field like a telephoto camera lens, it's a wide field. So it can see 100 times as much of the sky as Hubble can, but with the same sensitivity that Hubble sees. So every time we take a picture with WFIRST, we'll be doing 100 Hubble deep fields.
Wow.
Right. So this will let us do science that requires sampling a large piece of the sky. And the two prime sciences we're doing are the study of dark energy. We want to understand what is the dark energy that's driving the acceleration of the universe. And dark energy makes a very subtle impact on the distribution and shape of galaxies. So we have to look at a gazillion galaxies to add up all those subtle effects to really measure it well. So that's why we need the wide field for WFIRST to see so many galaxies. The other thing it will do is with that wide field, we'll be able to see those rare events when one star passes in front of another and amplifies the light through gravitational lensing of the back star by the front star. And if the front star has any planets, we'll be able to see the light amplified by those planets too. And this will be sensitive to planets that are out as far as Earth or Mars or Jupiter from their stars, whereas Kepler was more sensitive to stars that were more like Mercury, Venus, or Earth distance from their stars. So Kepler has told us what the innermost parts of planetary systems are like. WFIRST will tell us what the outer parts of planetary systems are out. When we combine the data, we will understand the demographics and statistics of complete planetary systems in our part of the galaxy. So those are two of the key things we'll do with WFIRST. We're just starting the design of WFIRST, haven't started building any hardware, and we're aiming for a launch in the mid-2020s for WFIRST.
That's amazing. So, you know, Hubble, the deep space photo is pretty much one of the most amazing things that you would ever see. I think it was the size of a quarter, and the galaxies that are in it. It's just a stunning photo. I can only imagine what 100 times that is going to be. It's really going to be something that I think again will shake up, you know, even the regular person. If you can see that and not be just stunned by what's out there and realize that that's still just such a small part of our universe and what we're out there to discover. I don't know. That to me is just, I've got chills a few times even talking about it.
Yeah, we'll be able to take a WFIRST picture and blow it up to the size of a room wall, and you'll
can I pre-order one of those to put on my wall?
Site set up, I'll send you the link.
that sounds great. So just really the last couple questions is, one of the things that I love the most is seeing you on stage at the Mars Society convention. You've been in this for quite a while, and you are still as giddy and kid-like as I am and most other people that love it, and it's something that's really stuck with you for all these years that you've been doing this. Hearing you talk about the discoveries throughout the universe, this excitement that you have is just, you can tell that it's a labor of love. So for those people like us that love to do it, what is your advice for really kids of all ages that are as excited as you are about the depths of space and want to follow in your footsteps in astrophysics, and just kind of follow this career and the amazing things that you've been able to see and do?
Well, you know, NASA is all about, well, you know, we're about science, we're about exploration, but we're mostly about making dreams come true, right? We dream of sending people to Mars. We dream of giant space telescopes studying the universe. We dream of rovers on Mars and landers on Europa, and just, you know, understanding everything. And that's the part of exploration that I love, and that most scientists and fans of NASA do. So NASA is always going to be looking for people who want to make dreams come true. People who want to work in areas where people have never done this before, want to solve either scientific or engineering or political problems that have never been solved before, and they have to have the technical skills to do that. You have to study your science or your engineering or your business management or your, you know, or your communication skills, or however you're going to contribute to humanity, doing something that is never done before and that we've been dreaming about for millennia. Right? You got to bring a skill set to it, and that's, you know, so if you've got the motivation, but you also have the technical skills, and that means, you know, schoolwork and education and experience, you know, working on these sorts of things. But if you bring that combination, NASA is always going to be looking for people like that.
And that's the amazing thing. I think one of the things I've learned the most about science is if you're willing to do the work and you have that passion and that love for it, the community is extremely welcoming. You know, I was just a regular guy, and everybody has been really, really great. And I've seen it so much. Kids and everything, it's we're really – this passion goes from people that are 6 to, you know, 90. You know, everyone that loves this, it seems like it's a lifelong thing, and I love the fact that NASA's always, you know, out there searching for the next group of dreamers, and that's the reason why we all love NASA, and we all look forward to the next big announcement. So I appreciate your time so much today, Dr. Hertz. Thank you for coming on and answering some amazing questions and raising the hair on my arms, and I'm sure on a couple other people's arms. And so thank you, and we appreciate your time today. And also, if anybody wants to get a hold of you, do you want to give them some websites, your social media contact, anything like that to finish up?
The website for our work is Science.nasa.gov/astrophysics.
Excellent. And we'll put it below. So do you have a Twitter handle or anything to get, if anybody wants to?
Yep, my Twitter handle is phertznasa.
All right, and we'll add that below so that way people can see it on the YouTube video if they want to say hey, or, you know, just thank you for your awesome time today. So we appreciate you, and thank you so much, Dr. Hertz, and everybody at NASA. Keep doing what you're doing.
All right, it's been fun. Thank you, Ron.
Thank you.